this video, we're going to talk about communication between a microcontroller and a PC using the USB bus. The reason why we want to do this is that there are many situations where we want to control some device or read from some real-world sensors, such as a temperature sensor or pressure sensor or whatever, and we don't have a convenient way to interface that device with the actual PC. PCs and application processors, such as the Raspberry Pi, provide a lot of processing power for things like computer vision and network connectivity, but they don't really allow us to directly connect to many real-world devices. A microcontroller, on the other hand, is designed exactly for this purpose. So a typical microcontroller will have many different types of interfaces, such as general-purpose I/O. This is the kind of interfaces we would use to read the state of a switch or control an LED. Analog to digital, which we would use to read from a bunch of different sensors, such as temperature or pressure. Digital to analog, which we would use to make waveforms or make analog values to drive other devices, or more advanced interfaces such as I2C or SPI. Nowadays, communicating with a microcontroller is pretty simple because a lot of microcontrollers include USB interfaces. Not all of them, but many of them do. When we use USB in a microcontroller, a lot of the times we're able to actually power the microcontroller directly from the USB bus, so the microcontroller doesn't need its own battery or power supply. It also provides bidirectional communication with the host PC, and it allows us to connect multiple devices at once. So as many USB ports as I have, I can connect that many USB-enabled microcontrollers. It also provides with electrical simplicity because USB only requires 4 wires. You have a power, ground, and then you have 2 data wires and very minimal external support circuitry. And they're also relatively low cost. So the Teensy 3.1 or 3.2 that we're using right now runs about $20, which is relatively low cost. Example applications for this would be robotics and mechatronics, which really rely on interfacing with sensors and driving, motors, servos, actuators. We can also do data collection with these devices because we can interface with so many real-world devices, and we could also use this for the Internet of Things because ultimately we're trying to connect real-world devices into a PC so that we can leverage its network connectivity, cloud connectivity, and so on. The microcontroller we will be using is the Teensy 3.2 USB development board. So this is directly taken from the manufacturer datasheet. It shows the pinout of all of the interfaces that come with the microcontroller. So you can see here that we have digital pins, that's general purpose I/O. This is what we would use to, again, read from switches or control LEDs. We have analog for reading from sensors, PWMs, which stands for pulse width modulation. That allows us to generate digital signals at a high speed so that we can control the speed of motors or create sounds using speakers. We have touch sense so that we can hook up capacitive touch sensors. We have serial ports so we can communicate through old serial type interfaces like RS-232 or RS-485. We have I2C and SPI, which are basically chip-to-chip communication libraries that we're not going to talk about just yet in this video. And we have other interfaces we can use as well, such as CAN. CAN is sort of an automotive type interface that's similar to I2C. We're going to be using the USB bus to communicate between our PC and our microcontroller. But it's important to talk a little bit about the different communication modes that USB uses. The mode that we're going to be using is called serial port emulation mode. This mode is an emulation of old school serial ports like RS-232 or RS-485. Those devices electrically, or those communication mediums, electrically are different. They use different voltages, they communicate over different lengths of wire. Some of them use twisted wire, some of them don't. But logically they work the same way. The idea is that if you want to send some amount of information in bytes, you send the byte one after the other in a serial train. So let's say that I wanted to send 3 bytes of information. I would send the first byte, then the second byte, and then the third byte. And the way that it works is that when you're sending an individual byte, you basically figure out the bits that represent that byte, and you generate a square wave bit by bit to represent that byte. So let's say, for example, I wanted to send 3 bytes of information. I would end up sending 24 bits of information or 24 high or low pulses, one after the other, to generate a pulse train. And when my receiving device got that pulse train, it would be able to decode that because it would know the rate that those pulses are coming in. That rate is called the Baud rate, and that basically tells us how often to sample that square wave to figure out what the logical voltage is, or what the logical value of that square wave is. So basically the idea is that you're generating bit by bit a digital representation of some amount of information, and you're parsing it on the receiving side because you know the communication rate or the baud rate, and you know what what voltage level means logical low and voltage level means logical high. Now in USB serial port emulation mode, the driver on the operating system is what actually establishes all this. So when we want to send bytes of information, we just start sending bytes. We don't have to worry about generating that digital signal. The nice thing about USB is that serial port emulation mode is defined by the USB specification. So operating system manufacturers such as Windows or Apple or the whole Linux project, they actually have this driver built in. So in other words, we don't have to install a driver for a USB device if we're using serial port emulation mode, because it'll already be supported by the operating system, which is really convenient. We programmatically interface with these identically to the legacy RS-232 port. So it doesn't really matter what programming language we use or how we set the port up. It's going to be programmed the same way. So we can use old code that uses an RS-232 port, and we can still communicate with a USB device using the same medium. The programming is exactly the same. Most programming languages support RS-232 or serial ports in general. Not all of them, but most of them. This type of communication also supports bidirectional communication and asynchronous communication. This means that we can both read and write from a device, or we can send and receive data to or from the device. And we also can do this in an asynchronous fashion, where we don't really have to have a clock pulse or any sort of synchronization pulse to make this happen. So in other words, when the remote device, such as a microcontroller, wants to send something to the PC, it just sends it, and it doesn't have to signal to the PC that it's actually ready to transmit data. There are methods of serial port communication that have these sort of ready to send and clear to receive signals, but we're just using simple USB serial port emulation, which doesn't require that. So it's also very convenient to program. And finally, we can implement a packaging scheme so that when we send multiple bytes of information at once, we know how to parse it. And we're going to talk about that later on. Other communication modes are human interface device, bulk transfer, and isochronous transfer. Human interface device is a mode that USB supports that is used for keyboards, mouses, and other human interface devices. So what this allows us is when we take a USB keyboard or a USB mouse, we just plug it in any computer and we don't have to install a driver. That's because the manufacturer of that keyboard and mouse implemented the human interface device communication class on that device. So basically what happens is that the driver is already installed on pretty much all available operating systems, so we don't have to install a new one when we plug in that new keyboard. That's why keyboard and mouse generally don't require new drivers when you plug them in. There's also bulk transfer. Bulk transfer is what a typical USB flash drive or USB hard drive is going to use. The way that this communication works is that it favors one-directional communication at any given time using large amounts of data. So in other words, when you have a USB hard drive plugged in, generally it's accepted that you're going to either copy a bunch of files to that hard drive, or you're going to be pulling a lot of information off that hard drive, but generally not really doing both methods of communication at once. Finally, we have isochronous transfer. Isochronous transfer is what a typical USB audio device is going to use. And the idea behind this mode of transfer is that when data gets lost, like let's say you're listening to some music on your USB headphones, if you were to drop a few bytes of information there, you may hear that as a little blip on the song that you're listening to, but you don't want that data to be retransmitted at a later time. So there are many different types of communication, like let's say in bulk transfer, you're copying a bunch of files to a USB hard drive. If you missed a few bytes of information, you would want to make sure that eventually that error was detected and those bytes made it into or back into the file that you copied. Otherwise, the file would be corrupt. However, if you're listening to music and you lose a couple of bytes of information, you may hear a little blip on the audio, or you may hear nothing at all. But if you were to retransmit those bytes later on, it wouldn't make any sense, because in chronological order, you would be hearing digital information from the music that might be a few seconds old or a few milliseconds old, and it just wouldn't make any sense. So isochronous transfer basically favors real-time transfer of information, and it allows for some losses. It doesn't try to go back and recover that lost information. Now, since we're going to be using serial port communication to communicate between the PC and the microcontroller, we need to figure out a way to send multiple bytes of information at once. On a regular serial port, you can just write one byte of information at a time. If you want to send multiple bytes, you have to basically train them together and send them all out as one burst of information. The problem with this is that that doesn't really have any information on when the information started and when the information ended. So let's say, for example, we have a program that we coded in maybe C++ or Java or whatever running on our PC, and we wanted to continuously send information to a microcontroller. And let's say that the information we continuously want to send is 2 bytes of information at a time. If we just stream out those 2 bytes, byte 1, byte 2, then byte 1, byte 2, then byte 1, byte 2, the microcontroller may miss one of those bytes at some point, and it doesn't know which byte belongs to which. So it may get byte number 2 first, and then byte number 1, and if it doesn't know when the start of that data transfer began, it doesn't know which byte belongs to which logical value. So because of this, we need to use what's called a packeting scheme. Packeting is basically when we take information that's related to each other. So in the 2-byte example, our packet may contain 2 bytes of information, and then we create some framing data around that payload of information that we have. This encapsulation of the payload data allows us to do things like error correction, determine when the beginning of a packet starts, and so on and so forth. So some requirements for our packeting scheme are basically we want to support variable width packets. So we want to be able to send 1 byte of information or 5 bytes of information or 200 bytes of information, and we want that all to be able to be encapsulated within one single packet. We also want to automatically detect the head of a new packet. In other words, when we start transferring information and we start creating the serial byte stream, we want to be able to receive those bytes on the microcontroller end and understand when a packet actually began so that we don't start parsing halfway through the packet and get misaligned. We also want to automatically detect and be able to recover from any dropped bytes. So it's possible with this communication that we get some interference on our communication wires, or maybe some electromagnetic interference or whatever, and we may lose 1 byte of information. If that happens, we want to be able to detect this situation and understand when we have a packet that may have lost some information. We also want to be able, similarly, to detect and recover corrupted bytes. So in a similar sort of situation, we may be transmitting 1 byte from our packet, but it's possible that 1 or multiple of those bits got flipped due to interference or electromagnetic interference or whatever. So we want to be able to detect either of those situations and understand when the data that we received from the microcontroller could be corrupted, because we don't want to control a real-world device on some communication value that may not be correct. So the solution to this is that we're going to build a packeting scheme, and it's going to include a start byte, which will signal the beginning of a new packet. We're also going to encode the length of the payload into the packet, and we're going to store the data in the payload after this header. So the header is basically just the 2 bytes, the start byte, and the length of the packet that sort of begin the framing of the packet itself. After the payload, we're going to encode something called a checksum, which will allow us to go through the data that we've received and check to see if we have any errors, such as drop bytes or corrupted bytes. A checksum is a strategy that basically goes through the data that we're trying to send. It generates a unique number or unique value that represents that data, kind of like a MD5 hash in like a large file transfer. And then we transmit that value with the packet so that when the receiving target gets that data, it will go back and recalculate what that checksum should be, and then it'll check it against whatever it received to make sure that those values are equal. If they're not equal, then that means there's some sort of discrepancy in the data and an error has occurred. So here's an overview of our packeting structure. First, we have the header data, which is going to be 2 bytes of information. The first byte is going to be the packet start byte, which I'm arbitrarily going to define as the hex value AA. You could choose any value here, but I chose AA because it visually pops out on a console when I'm sort of watching the byte stream in a debugging mode. It allows me to easily see when the beginning of a packet starts. Next, we have the packet length N, which is going to be the total number of bytes in the packet, including the payload and the framing data, which is the header and checksum. Next, we have the payload data itself, and this is basically going to be the data or the bytes of information that we actually care to transmit in the first place, minus the framing data. And then finally, we have the packet checksum, which is going to be a byte that we compute as a function of all of the other bytes in the packet. And this will allow us to basically recompute this on the receiving end and check it against the value that we received to make sure that they're equal. If they're not equal, then an error must have happened, such as a lost byte or a corrupted byte, and we should mitigate that situation using some other method. When we compute our checksum, we're going to apply a simple XOR chain over the entire packet. Basically what this is doing is iterating over the packet up to the actual checksum byte, and it's applying the XOR bitwise operation in a byte-by-byte fashion. XOR is just a bitwise operation that will compare 2 bits together, and then it'll return true if one and only one of those bits is also true. So in other words, if you have false false, XOR would return false. If you have true false, XOR would return true. If you have false true, XOR would return true. And if you had true true, XOR would return false. So what we do is we initialize the checksum value to 0. That initial byte will be initialized to 0. And then we'll iterate over all of the checksum bytes starting at 0 and then going to n-2, which is going to be the byte before the checksum. And then we will iteratively assign checksum to be the current checksum XORed with whatever byte is at packet at I. So this resulting for loop will basically give us a unique checksum, and then that's what we're going to store in the checksum value and transmit with a packet. On the receiving end, when we get that checksum, we'll recompute what the value should be, and then we'll check it against the one that we received. If they're not equal, then we know that an error has been detected, and we can handle that situation. Now we're going to experiment with the packaging scheme using a Raspberry Pi and the Teensy 3.2 microcontroller. We're going to load some example code on the course GitHub repository. So we'll go ahead and cd into the course folder, and then we'll do a git pull to update. So now that we have the up-to-date code, we're going to go into the Teensy folder, and then the example we're going to run is in the serial communication variable folder. That means serial communication with variable width packets, because that's what our packaging scheme supports. When we go into that directory, we'll see that there's a serial communication variable.ino. Remember, that's an Arduino project file, so we can go ahead and just load it directly into the Arduino IDE. So we'll go ahead and launch Arduino from the menu. Once Arduino is loaded, you can load the serial communication variable.ino file from the Open Project dialog. When you have the project loaded, you can go ahead and program this example. It should directly compile and go onto your microcontroller. So the way this example code works is it's basically listening for an entire packet to come in, and it does that by first listening for the hex AA. When it receives the hex AA, then it's going to check the next byte, and it's going to check the value of that byte, and then it's going to grab that many more bytes because it expects that next byte to be the length of the entire packet. It's then going to grab all the rest of the bytes that it thinks it needs to grab, and then it's going to use all the bytes that it's received up to that point to compute a checksum. It will then use the final byte that it receives and then check it against the checksum that it's calculated, and if they're equal, it will determine that it received a valid packet. When it receives a valid packet, it's going to toggle the LED, and it's also going to echo that packet back to the sender. So in other words, we're going to echo the packet back to the PC. So this is going to check not only the microcontroller's ability to receive packets, but also the microcontroller's ability to send valid packets back to the PC. So if you work your way through this code, you will see that there's a send packet function, and this send packet function is all that you need to actually turn a payload into an actual packet. So this will add the framing data. It'll add the hex AA, the packet length, and the checksum at the end. Then there's also a validate packet function, and this is what you would pass. So like let's say you were listening for serial bytes on your application. If you thought that you had a packet, but you wanted to actually check if it was valid, you would pass that to this validate packet function. And that would check for the hex AA, it would check the packet size, and it would also check the checksum to see if the collection of bytes you had was in fact a valid packet structure. Once you have the Arduino program compiled and flashed on your Teensy 3.2 microcontroller, you're ready to go ahead and establish communication and start checking out the packaging structure and testing it. So we're going to use a serial port emulator to do that. We could program our own user application in C++ or C or Java or whatever programming language that we want, because most of them will support serial port communication. However, for this initial stage, we're just going to use a precompiled program to actually create packets and send them and see if we get a response back from the microcontroller. The program we're going to use is called qtcom. So we'll do sudo apt-get install qtcom. And this will install the qtcom application. We can then run qtcom with sudo to make sure that we have permissions to access the serial port. If you set up the udev rules for the serial port correctly, you shouldn't have to do this, but just in case, we'll go ahead and run it with sudo. And this will launch the qtcom application. So a serial port by default will have some sort of name like /dev/tty s0 or acm0 or something like that. The Teensy in this case is named acm0, and I know that because when I went to my Arduino IDE here, I can go to port, and this will load all of the available serial ports on my computer. These ports will show up when I plug the USB device if it's properly programmed. So I know that my Arduino is named or has a serial port /dev/tty/acm0. So over here in QCOM, I'm going to make sure that I have that here. It may not show up in the drop-down dialog, so make sure that you, if you don't see it there, don't get discouraged. The baud rate we're using is 9600, and I've established that in my Arduino code here at the very top. Here, the baud rate is 9600. So that's not really all that important for a serial port emulated device, but we'll go ahead and set it anyway. We want to use 8 bits, 1 stop bit, and no parity. Those are by far the most common serial port settings. And then we want to make sure our handshake and reading and writing settings are set as listed here. So once that's correct, we can hit Open Device, and that'll establish a communication with the device. Now down here, these are bytes, or these are serial packets that I've transmitted previously. So this is the transmit window here, and up here is the receive window. So everything up here will be what's coming in from the microcontroller, and everything down here is going to be what I'm going to send. Now let's say hypothetically that I wanted to send the payload 1, 2, and 3. So I want to send the byte 1, the byte 2, and the byte 3. I would need 3 framing bytes to send that information. So the very first thing I would need was the hex AA, and if I go to this menu here and select hex input, that will allow me to directly enter hex characters, 2 characters per byte, per hex byte, to actually send that data in a hex format. So in other words, I would want to send AA because that's going to be the start byte. And then my length that I want to send is going to be 6 because I have 3 bytes of payload and then 3 bytes of overhead. So I'm going to enter 06 because the hex value for 6 is 6 in hex. That's simple enough. And then I want to send the payload bytes 1, 2, and 3. And I have to use 2 characters to express those. So I put the leading 0 there. And then I need the checksum for that byte. It's difficult to compute the checksum for this packet up in your head or by hand. So we're going to use a calculator to do that. If we go to accessories from the start menu, we can bring up a calculator and we can put this in a scientific mode and then allow us to, and set it also in a hex mode to allow us to do the calculation. So we'll click on scientific mode and then we'll click on hex, and then we want to enter the hex value AA, and then we want to XOR that with 6. So I'll click XOR and then 6, and then we'll want to XOR that with 1. So I'll click XOR and then 1. Then you want to XOR 2 and then 3. So XOR 2 and then XOR 3. And then this should be the hex value that's going to be the checksum for this packet. So we just manually computed the checksum that our program or our Arduino or Teensy would compute itself. So now I'm going to put the value AC here. And then this is the packet that I'm going to send. So once again, to recap, I have the start byte. I have the total number of bytes in the packet, which is 6. I have the first payload byte, which is 1, 0, 1. I have the second payload byte, which is 0, 2. And the third payload byte, which is 0, 3. So my entire payload is these 3 bytes of information here. And then finally, I have this checksum that I've calculated. So when I send this with the enter key, notice that I get a response here from the device. So that means that the device, and by the way, the LED flashed. So what this means, since I got a response, it means that the packet that I sent here was intercepted by, or was received by the device. It was determined to be valid, and then it was echoed back here. So let's say, for example, I computed the checksum wrong. So instead of AC, I'll enter in AD. That would be the wrong checksum. So I'm going to hit enter, and I shouldn't get a response here. So I'm going to hit enter now, and I get no response. That means that the microcontroller saw that packet, it received the hex AA, it received the 6, 1, 2, and 3, and then it got the checksum, and then it computed what the checksum should be and compared it against that value AD and saw that it wasn't correct. I can then switch back to another valid packet. So again, I'll enter in AC and then hit enter, and then I'm getting responses every time I send that value. I'm just hitting up and then enter to continuously resend that packet. Now there are other experiments we can do. So let's say that we change the packet length. We're going to go ahead and corrupt this packet and see what happens. So if we change the packet length to 5, I'm going to change that value 6 to 5. And what this is going to do is it's going to grab the hex AA, and then it's going to see that I have 5 bytes of information. So it's going to grab 3 more bytes of information because that's what's left in the packet. 2 in the framing data, and then 3 more bytes of payload that it thinks it needs to get, and then the final checksum. Or sorry, 2 bytes of payload, and then the final checksum. So in this case, in the wrong case, when I've corrupted this value here, I'm going to send 1, and then I'm going to send 2, and then the Teensy is going to think that the 3 value here is going to be the checksum. So it's going to see that, interpret it as incorrect, and then it's going to throw that packet away. Then the AC here is going to be interpreted as the beginning or the candidate for beginning of the next packet, but it's not going to equal hex AA, so it's going to determine that that is not a valid start character, and it's going to throw that packet away. So when I send this value, I expect it to not receive or to not send a response, and it's not. And then again, I can go back to a valid packet, and then I should get a response. And you can see here getting a response. Now let's try a situation where we again manipulate the length packet, but we increase that value. So what would happen here is that the microcontroller is going to see the AA, think that that's the beginning of a packet. It's going to see 7, so it's going to think that it has 5 more bytes of information to grab because we've already grabbed the 2 header framing bytes here. Then it's going to grab the 1, 2, 3, and then it's going to grab this value thinking that it's the 4th payload byte. Then it's going to expect 1 more byte of information to interpret as the checksum. So if I send this, I shouldn't get a response, and if I send it again, I should also not get a response. Because what happened there is that it thought that the next hex AA was the checksum for the packet that it was listening to before. So at this point, it grabbed this hex AA and then it ignored it because the checksum was invalid. And then it grabbed 7 and it was thinking that it should be looking for a hex AA and that didn't match. Then it grabbed 1. That was not hex AA, so that's also not the beginning of a new packet. 2 is not the beginning of a new packet. 3 is not the beginning of a new packet, and neither is AC. So then if I finally send a valid packet again, I should start getting responses again. So you can see here that this packeting structure is robust to failures whenever the checksum is incorrect or the length byte is incorrect or any of the payload bytes are incorrect because that'll affect the checksum.